After Lorentz boost from the rest frame, it does not have to be the rest frame, but a frame to another inertial reference frame that has the relative velocity v. This 4x4 matrix should be multiplied to the coordinates x0, x1, x2, x3 to obtain new coordinates of x1 prime, x2 prime, x3 prime. We use upper indices in here. Remember, if we use the relativity, you have to distinguish the two indices, but usually I only use the upper indices. Okay, that is identical to the CT XYZ in usual expression. If you look at the matrix, only the time and x coordinate, they communicate each other because the boost is along the x-axis. Okay. And beta is the relative velocity divided by the speed of light. Gamma is 1 over square root 1 minus beta squared. So as the beta goes to 0, it is rest frame, then gamma equals 1 exactly. As the beta goes to speed of light, v over c, if v approaches a speed of light, this is defined like that, approaches 1, it becomes 0, therefore it goes to infinity. So this Lorentz factor approaches infinity. So time dilation from the proper time tau multiplied gamma is the normal time. This one can be infinity. Okay. When v equals 0, beta equals 0, and therefore gamma equals 1. So time is collapsed to the proper time. And proper time tau is measured only if your measurement is placed at the same position. If an object is moving with velocity, then this time is not tau anymore. Moving clock shows t, and that t is gamma tau. Okay. What I'd like to study today is the integral over the space-time coordinate. After the Lorentz boost, some integral transforms to another. Before transformation, it should be something like that. After the Lorentz boost, the coordinates will be transformed in such a manner. Let's see. What is it? It is dx0, dx1, dx2, dx3, or ct, dx, dy, dz. And after the boost, the volume integral is dx1 prime, 2 prime, 3 prime, that is dct prime, dx prime, y prime, z prime. Remember, this one shows that you don't have to worry about this y and z components. They are invariant. So this problem is reduced to a 2 by 2 matrix case. What I'd like to see is what's happening for the area spanned by time and longitudinal coordinate is transformed into longitudinal coordinate and time difference after the boost, Lorentz boost. Okay. First of all, the final result for the differentials of the new coordinate can be directly computed from the matrix. And 0 and 1. This large 1 means diagonal elements are 1. And x 0 prime, 1 prime, 2 prime, 3 prime equals this product. In general, if I make use of chain rule, then differential of a variable is expressed as the partial derivative multiplied by this differential partial derivative with respect to x and multiply x difference, y, z, and multiply the difference in y and z. The same is true for every coordinate. So 1, 1, 1, 1, 1, 0, 1, 2, 3, 2, 2, 2, 2, 0, 1, 2, 3. Unprimed, 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 primed, 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 primed. Okay? In such a manner. As a result, what is the volume of the four-dimensional? I cannot draw in this picture. I can only draw the three-dimensional plot, but it is a four-dimensional parallel piped. I would like to compute this volume. That volume is just a product of this. And if I compute this product of this, at the end of the day, you will find this is nothing but the determinant of this matrix. Why? Let us simplify this relation into two-dimensional case. From xy coordinate to x prime y prime coordinate. And what I need to do is cosine, plus sine, minus sine, cosine xy. What is the volume? Dx prime, dy prime. What is the volume? Dx, dy is multiplied to cc minus ss. Multiply the matrix cdx minus sdy. With the sdx plus cdy. What is the volume? X prime y prime equals this product cdx minus sdy sdx plus cdy product csdx squared c squared dx dy minus s squared dy dx minus sc dy squared. Something wrong. Why? I just multiplied in a symmetric way. If I multiply this one in a symmetric way, it is just like a scalar product. It's not a scalar product. It is a vector product. It should be computed in an anti-symmetric way. Let's see y. It should be dx cross dy, where E1 hat, E2 hat. And cross product will give dx dy E1 cross E2, that is dx dy E3 hat. Aha! It should have been the cross product. Okay, let's do the job again with the cross product. C minus C dx E1 minus SD minus SDY E2. Cross product as the dx E1 and plus C equal cosine dy E2. If I make a cross product, I compute dx cross dy. C squared dx dy E1 cross E2. Here, minus s squared dy dx E2 cross E1. We have negative sign, but we have exchanged order. It is c squared plus s squared E3 hat. This is E3 hat. This is minus E3 hat. Therefore, it is E3 hat. I am missing dx dy. Dx dy. So dx cross dx, dy cross dy, this kind of contribution never appears. This kind of anti-symmetric product of every row, all of the row, using anti-symmetric nature is called the determinant. In the case of a 2 by 2 matrix, determinant is just cross one. C squared minus S, that is cosine squared sine squared equals 1. What about the 3 by 3 case? 3 by 3 case, we know how to do that. That is A1, A2, A3, B1, B2, B3, C1, C2, C3. Coordinates of the Cartesian coordinate with 3 vectors. This determinant is nothing but the cross product and the scalar product. That is a triple scalar product. Okay. And then extension to the 4 by 4 case is simply expressed in terms of epsilon ijkl matrix A, 1, 2, 3, 4, ijkl, sum of ijkl, and this anti-symmetric nature will give either plus 1 for the symmetric combination, that is even permutation, 1, 2, 3, 4, and so on. Minus 1 for odd permutation. By the way, our problem is quite simple because this determinant is nothing but the determinant of the 2 by 2 matrix. 2 by 2 matrix. Because this one does not contribute at all. It is identity operation. Determinant of this 2 by 2 matrix is a cross one. Gamma squared plus gamma squared, beta squared, what's that? I can factorize gamma squared, and they are inverse, reciprocal. It is 1 over 1 minus beta squared. 1 minus beta squared is 1. So determinant is 1. Okay, determinant is 1. Then our Jacobian is 1. So integral measure does not change at all. Actually, the basic reason why is that we can decompose into ct dx dy dz. Y and z are perpendicular to the relative motion. Relative motion is only along the x-axis. So this perpendicular direction is invariant. What I need to consider is these two factors, but on the Lorentz transformation, just like this, from the rest frame to moving frame, time dilates with a factor of gamma that is greater than 1. However, the longitudinal direction x contracts. That means this length contraction, time dilation, they are exactly canceling each other to make this two double integral over time and longitudinal direction to be invariant.